Hello everyone, thank you for joining DataCon LA 2020 and welcome to the emerging tech track, and it's quantum computing, the next new technology. Soon we'll be listening to Dr. Mark Jackson. I'm Lawrence Giglio, your host, and our co-host is Murali. We'll be moderating the chat and the Q&A, so get those questions in during the session. Today, our guest, Dr. Mark Jackson. He's actually a scientific lead at Cambridge Quantum Computing. He's got a PhD in theoretical physics from Columbia University and spent 10 years researching superstring theory, cosmology, and almost 40 technical articles. To promote the public understanding of science, he founded the science crowdfunding platform Fiat Physica and non-profit science partnership. He's also an adjunct faculty of Singular University and a director of Astronomers Without Borders. And I'm going to hand it over to Dr. Mark Jackson now.
Thank you. Thank you very much, Lawrence. It's great to be here, and thank you everyone for joining me here at DataCon LA. I'm sorry I couldn't join you in person, but I'm currently visiting Portland, Oregon, so it's great to be here. Let me share my screen here with you. Can you all see that there?
It's viewing.
Yes.
Great. So today I'm very excited to be telling you about quantum computing and all that it can do for you. And this is especially pertinent to a conference such as DataCon, because what you do with the data is certainly very important. And quantum computing has crept up in the past few years as really the next paradigm in computational technology. And you've probably even been seeing the past few months a lot of headlines about quantum computing. The progress has really been explosive the past few months. So I'm very happy to be telling you about that today. So just to very quickly give you a background about the company that I work for. So we were established in 2014, which actually makes us one of the oldest quantum computing companies. We now have over 120 employees all around the world, about 2/3 of whom are scientists specializing in quantum technologies. We have partnerships with all the major hardware providers that are actually building the quantum computers, such as IBM, Honeywell, Google, Microsoft, recently Amazon just a few days ago, and IonQ. So we focus on the software. We don't actually build the quantum computers themselves. We develop the software. IBM and Honeywell are investors in ours, and our focus areas are on quantum compilers, machine learning, chemistry, and cybersecurity. And so this is what I'll be talking about today. Kind of a very brief introduction to what quantum computing is, and then focusing specifically on machine learning and AI, what compilers are and how to get hardware access, and then finally cybersecurity. So this is a picture of the very first computer, as we would call it, which funny enough was exactly 200 years ago, and this was developed by Babbage in Cambridge, England. And even though it looks kind of antiquated by today's standards, it actually has all of the main ingredients that we would see in a computer of today. And this is a computer of today. In fact, this is identical to the laptop that I'm giving this presentation off of right now. And it looks so much slicker, and it is incomparably more powerful than the previous slide. But conceptually, it's identical. All of the components in the previous slide are in this. And this is because the basic way that you process and store information is identical. It's really just switches, which can be on or off, ones or zeros. And this computer does it much, much faster than the one 200 years ago, but the basic idea really hasn't changed. In fact, the first fundamental change in the way that we process information is from quantum computing. And I'll show you a bit about how that is now. So these are some of the words that you might have heard of with quantum computing. So one term is qubit, and this is short for quantum bit. And the difference is that whereas bits can be ones or zeros exclusively, a qubit can be a 1 and a 0 at the same time. And so it's this ability to be two things at once that's really at the core of why quantum computing is so amazing. Second term is entanglement. And so this is when one qubit, the value of it depends on the value of another qubit. And you may not know what value of either one is, but whatever one is, it will directly affect what the other qubit is. And this is a purely quantum phenomenon. There's no classical version of this. Superposition is the technical term for this ability for a quantum state to be in two states at once. And again, that's really at the core of why quantum computing is so powerful. It can be a 1 and a 0 at the same time. And then finally, quantum supremacy or advantage simply refers to the ability of quantum computing to be to do something better or faster than a classical computer. And it doesn't necessarily have to be interesting or useful. It's just the fact that you could do one thing with a quantum computer that you couldn't do with a classical computer. And it was actually last fall, about a year ago, that Google demonstrated this. And this is pretty well accepted in the community right now. So this means that quantum computers really do exist, and they really are to be taken seriously. Now, this graph is why quantum computing is so amazing. Every time you have one qubit, recall that that represents two states. But every qubit that you add doubles the number of the number of configurations. So one qubit represents two states, two qubits represents 4 states, 3 qubits represent 8 states, and so forth. So 30 qubits represents 1 billion different configurations all at the same time. And by the time you have 300 qubits, this actually represents the number of atoms in the universe. So that means that even in principle, you could never have a classical computer more powerful than that, because you would take the whole universe and you would build a computer from that. So this is why quantum computing is so amazing. With just 300 qubits, you could do things faster than an entire universe-sized computer. So why do we do this? Why do we go to all the effort of building quantum computers? So the idea is that we could reduce the computational speed or the number of samples needed to do certain tasks. And of course, if you can do more tasks, you can usually get a more accurate answer. And it's not just that, okay, this is a faster type of computer. The increase in speed is so overwhelming that we can do things that we never could have hoped to have done with a normal computer. And I'll be telling you about a few of those soon. So I don't want you to think that this is just like the iPhone 8 compared to the iPhone 7. It's not just an incremental increase in the speed or ability. This is a major overhaul in how we process information and what type of problems that we could tackle. They really do exist. This is not science fiction and fantasy and buzzwords and such. Quantum computers really do exist. Just in the Western Hemisphere alone, we know of over 100 hardware groups building quantum computers. So several of these names, of course, you'll recognize: Google and IBM and Intel and Microsoft and Honeywell and such. There's also a lot of startups building quantum computers. So Rigetti is based in Berkeley, California, and IonQ is a spinoff out of the University of Maryland College Park. And all of these pictures here that I'm showing you, these are actual quantum processors. These are not artist illustrations or something like that. These are actual hardwares that people are already using right now. This is the roadmap of progress. I imagine that most of you are probably familiar with Moore's law, which has observed that for the past several decades, we've seen the computational power for normal computers double every 18 months or so at the same cost. And that's remained amazingly consistent for the past few decades. There's something even more impressive in quantum computing. So there's something called the quantum volume, which is sort of a single metric corresponding to the overall power of quantum computers. And this was developed by IBM. And IBM has doubled the quantum volume every year for the past 5 years or so. So that's the blue line here. So every dot there is an actual data point representing an actual quantum computer. Now, that's amazing that it's doubled every year. What's even more amazing is this orange trajectory by Honeywell. And so Honeywell has been on a much faster trajectory. Just a few weeks ago, they put out a quantum computer with a volume of 128. And so this is great. And furthermore, Honeywell believes that they can increase this progress by a factor of 10 every year for the next 5 years. So by 2025, they believe that we'll have quantum computers 100,000 times more powerful than the quantum computers that we're seeing today. Now that would be amazing, of course, in itself. But just a few weeks ago, there was another announcement by this startup, IonQ, and that's that yellow dot that I put at the top here. They claim that they soon, in a few months, they will have a quantum processor with a quantum volume of 4 million. And of course, this is several years ahead of schedule. And so it would be amazing if true. I've only put an asterisk there because this is what they forecast to happen in a few months, and it hasn't been tested by outside groups, and we haven't seen an article yet. They're a fantastic group, and I have no reason to doubt this. It just hasn't been tested. And so you see a lot of progress has been happening, especially the past year. And this is quite a bit faster than we imagined just a few years ago. So what do you do with a quantum computer? What are the problems that we hope to tackle? So this is a very brief summary of some of the things that we believe that we can be tackling. So one of the first applications was chemistry, designing personalized medicine and better material science. Unfortunately, I won't have time to focus on that today. What I'll be talking about today is more on the information technology and the finance side, because that deals more directly with data and how to protect it. So I'd first like to talk about quantum machine learning and AI. So I'm sure that many of you are very familiar with machine learning and AI. And even though there's a lot of different approaches that have been developed now, they all have one thing in common. And that one thing is that they're all based on probabilities. So probabilities are just numbers between 0 and 1. And what machine learning does is it takes past data and it develops some rules for trying to predict the future values of things and calculate their probabilities. So it uses these probabilities of past data to make predictions. And when it does the calculations, it's not that difficult because probabilities, again, are just numbers between 0 and 1. Now, quantum machine learning, on the other hand, is completely different mathematically. It's not just faster machine learning. It's a fundamentally mathematically different tool. Quantum machine learning is based on something called an amplitude, which you can think of as an arrow or a vector. And the difference with arrows and vectors is that when you add them together, it's very important what the relative angle between them is. So unlike probabilities where you simply add them, with vectors, you have to think about the relative angle. So in this picture right here, you're adding the head of one to the tail of the other. And you see that because they're roughly in the same direction, you get a longer resultant vector. Now, if they happen to have been in opposite directions, they would cancel each other out. And so you get a resultant 0, which would be impossible. You could never add two probabilities together and get 0 unless each of them was 0. So the mathematics of quantum machine learning is much more sophisticated than classical. And so, so we expect that this will lead to much more sophisticated decision making and would be able to pick up on patterns that we normally never would have seen with classical tools. So what can you actually do with this? So of course, a lot of the immediate applications have been in finance because any sort of quantitative tools are very beneficial, and a lot of financial groups have the money to invest in this right now. So one thing that we've already identified is speeding up simulations using Monte Carlo type approaches. And so this is when you don't know what something is going to do, like you don't know how a stock is going to react. So you run a lot of simulations and you kind of look at what the average is going to be to try to predict what's going to happen. Now with quantum machine learning, we've actually found that it has a quadratic improvement in speed. So for example, if you need to run 1 million simulations classically to get some sort of desired accuracy, with a quantum computer, you only need to run 1,000 simulations. And so that's the dramatic speed up that you see with quantum computing. And again, this is already being studied right now by a lot of major financial groups, and we have a lot of partnerships with some of these groups. So we're very familiar with this. A second application in the financial world would be optimization. And so this might be arbitrage. This might be some sort of portfolio that you have where you're trying to minimize the risk given some sort of parameters or something. And there's actually exponential speed up for some applications of optimization. And so again, this is being very much investigated right now. This is just a very quick summary of some of the financial groups that have been getting into it. These are just headlines from the past year. So a lot of groups have been setting up their own quantum computing groups, and others have been hiring quantum computing organizations such as CQC. Now, what would be an example of a quantum machine learning type of problem? So this is an example that we had worked on in the past called the knapsack problem. And so this is when you have like a knapsack, you have some finite capacity. So let's say in this case, you can carry 13 units of weight. And then you're given some items of value, and they have different weights and they have different values. You're trying to maximize the value that you can carry with you, subject to the constraint that you can only carry so much. So this is a very ubiquitous problem. This comes up all over in for example, like scheduling and industrial logistics and such. And the reason that we study this is because it's very well known how to tackle this with classical computing. It's difficult if you have a lot of items, but there are well-developed heuristics. And so we did this on a quantum computer to compare this to its classical counterpart. Now, even though quantum computing is great for speeding up problems, the trade-off is that you aren't necessarily going to get the right answer. And so in this example, you see on the horizontal axis, you see all the different possible outcomes. So the 0 means you don't have an item, and the 1 means you do have the item. So, so on the left here, this is the 5-qubit example. So we had up to 5 different items that we could consider. And you see that each of the different possible combinations of having which item is considered. And the correct solution is standing out there. This is what you are most likely to get at the end of the quantum computing simulation, but it's not guaranteed to be the answer you get. And that's very typical of what quantum computing algorithms do, is that there's speed up, but the trade-off is that you're not guaranteed to get the correct answer. So what you'll probably have to do is run the simulation a few times to make sure that this really is the correct answer. On the right-hand side, this is the same problem, but with 10 items, and this was run on a 10-qubit simulator. We just haven't done it on an actual quantum processor yet. This actually represents the state of the art. No one has actually done this on 10 qubits before. And so this shows how nascent the field really is. People are just now developing some of these algorithms. So a second thing that I want to talk about is a quantum compiler and how to get access. So many of you might be developing quantum algorithms yourself. Just like a classical computer, you have to have a compiler. So you write your program in a quantum language, but then this has to be translated into instructions for the actual quantum computer. So you have to actually manipulate the qubits and such. And so that's what a compiler does. So it takes the code that you write and turns it into instructions for the quantum computer. And ideally, you would like to do this as efficiently as possible. And this is especially important now for a reason that I'll explain. So Cambridge Quantum Computing has developed a compiler which we call Ticket. And if you're familiar with quantum mechanics, you'll understand the notation here, but we call it Ticket. So any of the major quantum computing languages that are available by IBM and Google and Microsoft and such, you can use those and you write your code. Ticket will automatically find the most efficient way to compile it for the hardware that you want. And so this could include the IBM or Google or Microsoft or Honeywell or Amazon or what have you. You simply select on one line of your code which hardware you want, and Ticket will automatically take into account all the nuances of that architecture. And if you want to run it on a different hardware platform, you simply change that one line. You don't need to completely redo your code. And that's a problem that people have if you try to do this in, say, Circ, the IBM language, and you wanted to move it to Google's, or sorry, Circ is of course Google's, and you wanted to move it to QuizKit, which is IBM's, you would have to completely rewrite it. And Ticket does that for you. You simply change one line. And one reason that this is especially important nowadays is because we're dealing with what are called NISQ quantum computers. And NISQ stands for Noisy Intermediate Scale Quantum. So this means we do have quantum computers, and they have 50 to 100-ish qubits, but these have high error rates, and there's no error correction. And so you kind of have to just do the best that you can with a NISQ type of quantum computer. So this makes running the most efficient quantum code that you can especially important. And so that's why a lot of people have been using Ticket thus far. One approach that people have been using is to use what are called hybrid algorithms. This means that you have a quantum algorithm and a classical algorithm, and each manages some part of the problem. And which part depends, of course, on the specific problem. but you do as much heavy lifting as you can with classical computers, because these are much more well developed, and you send one smaller component, the part which most benefits from quantum computing, to the quantum computer, and then at the end the results are synthesized together. We've just a few weeks ago we had an upgrade to take it so that it now supports the Honeywell, AWS, and IonQ type platforms. If you are interested in using this, I'm happy to speak with you. If it's just for your own personal use, we can give you that for free. You can get it from GitHub. If you would like an enterprise type solution, we're happy to discuss that. We have both R&D and enterprise deployment type licenses. But of course, just using a compiler doesn't mean that you automatically have access to the hardware. If you'd like to discuss how to get access to IBM's premium machine, we're happy to talk with you about that. CQC is uniquely able to give you 6 months access, sharing it with 3 other groups. And this is in contrast to if you went directly to IBM, it would probably be a multi-year contract for quite a bit more. And so we're uniquely able to give you access in the short term. So the final thing that I'd like to speak about is cybersecurity. And this is usually the one thing that people know about quantum computing, is that it has something to do with hacking. And that's true, and I'll explain why that is. So this is the reason that most of the time we can safely send information on the internet. This is because we don't send sensitive data like credit card numbers itself. We send an encrypted version of that information. We use some sort of complicated mathematical formula to encrypt it, and we send the encrypted version, and the person on the other side decrypts it using a key, which is a unique number known only to them, hopefully. And this has worked very well for several decades, and that's because the mathematical formulas that we use are so complicated that normal computers would only be able to undo them if you had like a supercomputer for millions of years. And of course, that isn't practical. It would be difficult to get access to that, and if you did, it would cost you far more than the value of whatever you were trying to decrypt. And so that's why most of the time encryption works pretty well. That's unfortunately changed because of quantum computing. And the reason for this is because it turns out that the formulas that we chose a few decades ago to do the encryption, it turns out that they're very easily solved by quantum computing. And this was realized some time ago, about 25 years ago. No one really took it very seriously back then because there were no quantum computers 25 years ago. But the progress shown in the past few years has really concerned people. And even though it's not possible today to use quantum computers to hack things, it could be possible in just a few years. And so that's why people are thinking about this now. Now, on the top half of this slide, these are about 99% of online encryption tools being used on the internet right now. And they're all vulnerable to quantum computing. And so you might recognize RSA, for example, as something which is kind of ubiquitous in encryption. So that's very vulnerable to quantum computers. Now, the bottom half of the screen, these show what are called post-quantum encryption algorithms. So these are other formulas which could be used for encryption, which are not thought to be vulnerable to quantum computing. And I want to emphasize are not thought to be, because the truth is that we don't know. There's a contest going on right now. It's hosted by NISQ, the government agency. They invited people to submit their ideas for what these quantum proof algorithms could be. And actually just a few months ago, NIST unveiled the final 7 candidates. So for the past few years, hackers have been doing their best to undo these algorithms using quantum computers. And so there's kind of 7 which have withstood the tests. And so the final winners, there will probably be 1 or 2 winners, those will be announced in the next few years. So as I said, the good news is there's already several post-quantum algorithms which have been developed. The bad news is that upgrading takes time. It's not as simple as upgrading and 5 minutes later everything is secure. If you've ever tried to upgrade any sort of serious security system, you know that it can take months or even years to do this. You have to deal with a lot of legacy systems, and this has to be done by a lot of people over great geographical distances. And so that's why I would strongly encourage you to think about this now. Don't wait until you've been hacked to start worrying about it. These post-quantum encryption algorithms are available now. They're in the public domain. And so there's really no excuse for doing that. Now, there's a related technology, which is an inherently quantum technology called quantum key distribution. Now, the basis for this is this video here. So suppose you had a source of entangled particles. So that again means you don't know what the state of these qubits are, but whatever it is, they're identical. And these are independently measured by two observers. We'll call this Alice and Bob. So Alice measures her qubit in a random direction, and Bob measures his in a random direction. And they get some answers, and they record each of their answers. And then at the end of this, Alice and Bob will compare notes on which directions they measured in, not the results, just the directions. Now, because these were entangled particles, if Alice and Bob measured in the same direction, they should always get the same answer. And so in that way, they can securely communicate a key, which they can use for encryption later. But now redo that where there's some sort of eavesdropper, we'll call her Eve. Eve intercepts one of the qubits, measures it, and then tries to be sneaky and replaces it. Now, if this were classical physics, that would be the perfect crime. Alice and Bob would never know it's been replaced. But notice that because of the entanglement, there is something different. You notice that they're no longer entangled. And so when Alice and Bob do their measurements, even if they measure in the same direction, they will not always get the same answer. And so you'll see now when Alice and Bob compare, when they do the comparison, even if they've measured in the same direction, sometimes they will get the wrong answer. They get different answers, and that means that there's something wrong. And so that means that Alice and Bob can do a quick test run. They see that there's been some sort of tampering or eavesdropping, and they just call it off. They set up some different communication channel. So you see this is a new type of communication, which is purely quantum. And even though it seems like something like science fiction-y, it actually already exists. There are several networks which have already been established. China and Switzerland have already set up extensive QKD networks, and we're starting to see this even in America. So this is something which is up and coming right now. In fact, even just a few months ago, the U.S. government announced a major investment for this. So this is coming from the Defense Department right now. So a quick summary, quantum computing will definitely have a lot of benefits, but people should be aware of the risks and know how to protect against them. We think that in as short as 2 to 3 years, we could start to see advantages from quantum computing, like actual commercial advantages from algorithms built for quantum computers. It takes time to develop these. This is not a matter of coding something in Python and in a few weeks you have some beta version for your app. It really does take time because we're starting from scratch for these quantum algorithms. So we encourage people to start this now, develop sort of proof of concept type of projects, and then in a few years, as the hardware gets better, you'll be in a very good position to take advantage of this. In terms of how to work with CQC, this is what we do. We work on proof of concept type projects. Again, if you already are developing your own quantum algorithms, we're happy to speak with you about using our compiler or providing access to the IBM or Honeywell machines. So that's it for my prepared presentation. I'm happy to stick around and answer any questions which you might have.
Thanks, Mark, for your excellent presentation. Very interesting.
Lawrence.
And I think we have 2 questions in the session question and answer room.
Right, Lawrence. The first question, Mark, somebody wanted to know if quantum volume is equal to the number of qubits.
That's an excellent question. No, it's not. So a few years ago, people were very focused on the number of qubits. That's a very obvious way to measure the power of a quantum computer. And people correctly started pointing out that that's not really fair because qubits were still, and still are, pretty noisy in that the error rate is pretty high. So it was sort of like 1 in every 200 operations that you would do on a qubit, you would simply get the wrong answer for a variety of reasons, but you would simply get the wrong answer. So imagine how difficult it would be to program a computer if every 200th calculation it did gave the wrong answer. And so strictly going by the number of qubits wasn't really a fair metric. And so this is why about a year or 2 ago, IBM introduced this quantum volume, which is a complicated arrangement of different data. So it does take into account the number of qubits, but it also takes into account the error rate of the qubits. It takes into account the coherence time. So it's a very complicated formula, which I can't give right now.
Mhm.
But it's a much more fair measure of the power of a quantum computer.
Great. That was a question from Anthony Hogger. The second question I have is from Jason Kang. Why does Eve has to replace the quantum bit? Why not just observe it like Alice?
Sure. So I'm assuming Eve is trying to be sneaky in this, and so if Eve simply measured the photon and that was it, then that information isn't very useful. So to get anything useful, Alice and Bob, remember, they have to compare notes on which direction they measured the qubit in, and only if they measured in the same direction are they assured that they will have the same answer. So if Eve just measures it and doesn't communicate this or anything, then it's kind of useless information. So I'm assuming that Eve is trying to be sneaky and get as much information as possible. So she would try to replace it, thinking that Alice and Bob won't know that it happened. But of course, by doing that measurement, she's destroyed the entanglement.
Cool, thanks. This is again a question from Anthony Hogger. Actually, this is my question as well. Trying to understand the roadmap, the future. So the question is, do you believe quantum computing will ever enter the mainstream, be in an individual's home, like current computers, et cetera, et cetera?
Absolutely. And I think it's going to happen a lot faster than, if you had asked me that question a year ago, I would have said yes in maybe 10 years. I think now it's going to be more like 5 years. I don't think that most people will realize that are interfacing with a quantum computer. I think it'll be something like you'll use Google Maps to ask directions on how to get somewhere. That's the type of problem that a quantum computer would be good at. So without even realizing it, you will have access to a quantum computer, which will do this route calculation and then send you the answer. Yeah, so I think it's going to be a lot of things that we're just not aware of, which will be used by a quantum computer very soon.
Is quantum computer, my question, Mark, is quantum computer more software or more hardware? And if it is a combination, do we have the hardware ready for the software?
Yeah, that's a very good question. So it is both. So quantum computers are very different from normal computers. That's why right now you might have seen pictures. They look like big chandeliers. One particular type, they look like chandeliers which are being lowered into giant freezers and kept at near absolute zero. Not all of them. Other types, they just look like big lab benches with wires coming everywhere. So right now they're very big. They're in labs. Only engineers and specialized professionals know how to use them. They're getting better, certainly. I've showed you the progress chart. Both are being developed. In machine learning, for example, just in the past few years, we've developed some basic techniques for how to do machine learning. And so we're kind of developing the software right now. And then in a few years, hopefully things will be at a point where we'll be able to have a commercial advantage from this. Yeah,
so recently, like in the last 1 month, I've seen Amazon post jobs on quantum computing. So I'm just wondering, how fast is this going, and where is this heading, and how relevant would it become in regular software engineers' lives like ours, and how do we have to adapt?
Yeah, so it's there's definitely been a huge hiring surge. For example, when I joined CQC just over 3 years ago, there were about 10 serious startups in the Western world that I was aware of. There's over 300 now. I can't even keep up with them. It's like every week I hear about some new startup being funded, or some major new technical advance, or some new major commercial engagement. There's a huge amount of money going into this. Companies can't keep up. They can't hire fast enough because there's not many people who have the background in physics to do this. I know there's a lot of like boot camps where if you already know a little bit about computers, it's not that hard to learn one more language or learn some new development tool or something. But programming a quantum computer is completely different. The logic is completely different. And so so it does take some training in quantum physics.
Quantum physics. So we still have about 5 minutes. I don't see any more questions. Oh, hold on. Yeah, I don't see any more questions. I'm going to ask a couple more questions if that's okay with you, Mark.
Sure, of course.
So how would a person enter the quantum computing ecosystem now?
Sure, that's a good question. So there's a few newsletters which I would subscribe to. So one is, there's one by NASA Ames. So you can subscribe to that. One is by Oak Ridge National Laboratory. And again, that's public. You can simply subscribe. There's a great blog called Quantum Computing Report. And it's focused more on the business aspects. It's not very technical. And so I think it's pretty accessible to non-specialists. There's another blog by Scott Aronson, who's a physics professor at UT Austin. It is pretty technical. So I would do that. I believe IBM has some sort of course or online certification or something. I've seen people post about that, but I haven't used it myself. I think I've seen MOOCs like Coursera or edX offer things. I think MIT offered some sort of quantum computing course. Yeah, so there's a lot of tools now being offered to people who want to get into this.
Mark, I have one more question from Jason Kang. He asks, what are some problems that quantum computing is not good at?
Good. So so quantum computing is not good at things where you need a definite answer. So for example, accounting software, I don't think it would be very good because you want to make sure that when you add these numbers up, you get the correct answer. And normal computers are very good at adding numbers. That's pretty simple. And so quantum computers would never be used for that. What quantum computing is good for is when you have a lot of possibilities and you need to quickly arrive at an answer which is very nearly correct. So in the example of like Google Maps finding a route, even if it's off by a little bit, that's okay. That's still a very useful answer. But in accounting software, you really need to have the exact answer. So so quantum computing would not be good for that type of problem.
Thank you. I don't see any more questions. In case the folks have questions, and this is an interesting, topic. It's new, it's fresh, and more importantly, a lot less literature is available out there, and only experts like you can teach us. If the team or the people are going to reach out to you, through the WUA app, and hopefully you can answer them. I have one question pop up. Nikita. Oh, I can't pronounce the last name. I don't want to butcher it.
Yeah.
So she asks, can quantum computers be used to mine Bitcoins?
That's a question I get asked a lot. So the answer is no, they cannot be used to mine Bitcoin. In fact, there was a study just recently on exactly that topic, and the answer is no. The mining operation is not something quantum computers are good at. What is an issue is that the encryption used for Bitcoin and blockchain and such is very likely, depending on the cryptocurrency and such, it's very likely the normal type of encryption, which is vulnerable to quantum computing. And so although you couldn't mine Bitcoin, you maybe could steal someone else's using a quantum computer. And so cryptocurrencies and blockchain and such will need to be upgraded to post-quantum encryption.
One more question from Anthony Hogger. Do you see quantum computing being able to figure out the solutions for P is equal to NP problems, or is that a limitation of human understanding?
So for those of you who aren't familiar with it, so there's a classification of how difficult problems are. And so there's problems where you can quickly verify an answer, even if you couldn't quickly solve it in the first place. And we don't know if that's true. Maybe there's some trick that we're not aware of to quickly solve these difficult problems. So I don't think quantum computing can solve that. But this is a great question because people are starting to think about a new type of classification called quantum hard, which is maybe it's difficult for a normal computer to solve, but it's easy for a quantum computer to solve. And are there strict mathematical guidelines on which problems are which? And we don't know the answer to that. We're just starting to figure out what those divisions are. And so this is very much an open question.
Well, thank you for the questions. And Lawrence, take it over, sir.
Yeah, thanks, Murali, and thanks again, Dr. Mark Jackson from
Thank you both,
Cambridge.
and thank you everyone for attending. If you have any further questions, feel free to get in touch with me.
Yes, please contact the speaker and provide your comment and feedback to us as the organisers or the community board, or you can start a discussion there to connect with others in the DataCon LA 2020 community. Thanks again for joining today's presentation. I hope you have gained some insights from the session. I'm sure you have. Great questions. Have a wonderful day or night. Thank you for being part of this year's DataCon LA 2020, and bye for now.
Thank you.
Thank you.